So yeah, we're going to talk quite a lot about reversing Flutter applications. I don't expect all the audience to know about yet Flutter and Dart, so this is the first thing we're going to dig into a little bit, and you'll see it's actually quite interesting, a really interesting concept behind it. Before that, well, my name is Axelle. I work as a security researcher at Fortinet. More precisely, I'm a mobile malware analyst and an IoT malware analyst, which means that I get malware and analyze them and try to detect that. And I'm also the organizer for the phone CTF, which is another on-site CTF, which is in the south of France, and it's dedicated to smart objects. So if you like the CTF tonight at BlackAlps, well, you're more than welcome to come and join us. It's at the end of November, November 24 and 25, in the south of France, if you feel like going there. Last but not least, it looks like LaTeX is used less and less, but those slides were generated with LaTeX. I'm kind of a little bit old school on that, but hopefully you'll like them, and the content hopefully as well. So this is a quick audience check after yesterday's dinner party. So who feels like this on the slide? Raise your hands. Okay, not that much. Well, actually, I'm not concerned by those who raised their hands, but those who didn't, which is the largest part, because it means that either you're still really totally sleeping or not aware that you're in that stage. Hopefully, I hope it's better. We'll see that. We'll dig into Dart. So Dart, it's a programming language. It's object-oriented, and it has a syntax which is very close to C or Java, depending. This is a working example, which is, I guess, pretty simple. You'll understand pretty quickly that it's just drawing two kind of lines, separator lines, and in the middle saying welcome to BlackAlps 2023. Okay, so pretty straightforward. Yesterday we had a talk about you shall not pass. Well, today I'm giving you one code to rule them all. And you are going actually with this previous Dart code, you are going to be able to compile natively this code to many different platforms. So it can be Android, iOS for the mobile ones, but also Linux, Mac, Windows, etc. Okay, with a single code, which means, of course, that you don't have to maintain different versions of your code, which is really helpful. Most of the time it's good. When it's for malware, it's not. But that's the downside of it, let's say. If we take again our previous example, well, I compiled it on different platforms, and well, what you can see there is that, well, I compiled it for x86 64-bit, ARM32, and ARM64. It's, again, what's really important, it's not like virtual machine stuff, it is compiled natively for each platform. Okay? You might also have noticed this extension, AOT. Well, it's just an extension. You can actually name the files whatever name you want. No problem with that. But it means, of course, ahead of time. And this is because with Dart, you can choose the formats of the executables that you wish, depending on if you want something which is very small or not, or if you want something which goes fast or not. So you can have different kind of formats. One which is called kernel snapshot, just-in-time snapshot, ahead of time, or just a self-contained executable there. We're going to talk a little bit more about those later. Flutter, it's just like a framework which is on top of the Dart programming language, and it's the user interface framework basically for that. So you'll have all the user interface, APIs, libraries, widgets, and you also have some build tools. And in our case, what's important is that you have built-in obfuscation. So we'll deal with obfuscated code on top of that. The execution format that Flutter has selected among the ones that I showed previously is first for debug releases. They're going to use what is called a kernel snapshot. I'm not sure that the name is that well chosen, but that's the name which is there. And this one is fully portable. And if you have to reverse a debug Flutter application, well, then you can be very, very happy because actually you will find nearly close to the source code, and this is really easy to reverse. No problem with that. Now, the issue is more with the release versions that we are going to deal with today, which are called the AOT snapshot format. And those are really much more complicated to deal with. They are obfuscated by nature, but by default by Flutter. And, well, we'll see that there are some other problems even there. So yeah, to deal with those Flutter release applications, well, I could have introduced you with all the concepts of Flutter or Dart and how to deal with that, but we're going to deal with it through an example, and hopefully it's going to be a little bit more visual or more understandable to get. So we're going back actually to last year's editions of Phone CTF, where I created a challenge where I implemented the Wordle game in Flutter. Well, when I said I implemented it, I didn't do that much, actually, I'm boasting. I mainly took a library which was doing nearly all the work, and I inserted flags in that. It was a two-stage challenge. The first stage was really simple. You can go and have a look at the write-ups, which are there if you want. And stage 2 was meant to be difficult. I wanted people to have to do some Flutter reverse engineering. Unfortunately, I did an error in there, and what happened is that people managed to get the second flag, which was a little bit more difficult, but without digging into the reverse engineering of the Flutter code. So they got the flag, of course, but I was a little bit disappointed. So I decided to create a stage 3, in where this time I fixed the error I had made in stage 2, and this time, well, I think there's no other way to get the stage 3 flag without reversing the application. I released that in January this year, and it was unsolved. We're going to solve it today, all together, to see what we have to do to get this third flag. In terms of coding, it's really extremely simple. I haven't done anything that was complicated because I knew that already reversing the Flutter application would be quite difficult. So I didn't want to add any difficulty. The stage 3 flag is encrypted in the application, but it's really basic encryption. It's just no, I was going to say that. No. It's hidden in there, but it's only 14 lines of code, basically, just to decrypt the flag. Okay, so really nothing difficult. So first thing is you get the application. And what are you going to do? So it's an Android application. If you're a little bit used to reversing those, it's pretty simple. You unzip it. In there, you notice that there's a Dalvik executable, which is named classes.dex. And that is normally where you have to dig in a little bit more, except that in this case, as it is a Flutter application, well, it's useless to go and have a look at this one because it will only have all the glue to go and start the Flutter environment. Where you have to go is, as we said, it's compiled natively, so you have to go in the native libraries and to find the code that we wrote in Flutter. So it's compiled natively. I compiled it to actually 3 different platforms because, I don't know, I felt that maybe participants ought to have a little bit of choice. So you can actually select the platform that you wish. It's going to be exactly the same, except, well, it's different instructions, but it's the same code behind it. And whatever platform you choose, after that you have inside that 2 different libraries, libflutter In there, it's the implementation of Flutter, so not interesting either for the challenge. What's really important is the last one, of course, libapp.so, where you have all the Dart payload, what the code that we wrote is going to be inside that. So what's that? Well, libapp is an ELF executable, so you can actually, if you want, parse a little bit the format of it. I don't know if you know mhex. Mhex is a little bit like, I'd say, 01 editor, if you know that. So you can parse. It's like an hex editor, but you can also apply a pattern to recognize the various parts of an executable according to a given format. So if you get into that, I also wrote a pattern for Dart AOT snapshots. And if you put to your library in there, you'll see that there are actually 2 AOT snapshots in libapp.so. You can also see that if you run objdump, it will tell you actually that you have, a VM snapshot and an isolate snapshot. So what's isolate? Well, basically it's, each isolate has its own event loop and the memory stack and memory heap. So it's used for the applications. For instance, you can have in there, I don't know, like the user interface. And if you have some background task and you don't want it to be blocked by the user interface, well, you put that in a different isolate. So it's a bit like threads, except it's not exactly the same architecture, but it's a little bit the same idea. Okay? So our code, of course, is not going to be in the VM snapshot, but in an isolate snapshot. And if you want to parse your libapp.so to see exactly where the isolate snapshot is, well, I've also written a tool for that, which is going basically to parse the ELF and tell you, well, at that point, this is the isolate snapshot where you should look into. Now, when you're in a CTF, you go a little bit maybe faster than that. The first reflex that you'll have, I guess, is just to run strings on it. Okay, so you run strings on your application, on your library, and you find the stage 1 flag. Okay, actually, there was even another way, a simpler way to get that stage 1 flag. But the issue here is that we want to solve stage 3. Okay, not stage 1. Okay. And of course, stage 3 flag is not in there, so we're gonna have to find it. And to find it, we are going actually to start with the stage 1 flag and try and find where this flag is used in the code. Okay. And hopefully, if we see where this flag is used, well, we'll probably maybe see where other flags could be, or I don't know. It's the first guess that we could make. So you throw it in a disassembler. This is radar. And I'm looking here. This is the instruction to the commands to find the flag that I am, the stage 3 flag. So there it is. And then I am looking for cross-references, so people who are using this flag. And, well, you get nothing. So looks like nobody is using this flag. And by the way, the result, if you're using IDAPRO, if you're using Ghidra, it's the same. Okay. All disassemblers there are lost at this point. So if we can't find the string, maybe I thought, well, maybe we can, I don't know, get some help from the names of the functions in there. So if you use normally some Dart code, you will get indeed some function names, and that might be helpful, except here it's a Flutter application, and I told you we have some obfuscation, and the names are obfuscated, which means that you're going only to get this. And well, good luck. You've got lots of functions. If you feel like parsing them all, well, you probably, it will probably take a little bit of time before you get to the right one, but, well, whatever. So why isn't it finding that string? Well, basically it's because in Dart, Dart is using an object pool where it stores all the objects that it uses quite frequently, or all the constants, the strings, and everything. So at some point in that object pool, which is like just a big table, we've got our stage 1 string at a given index, and if we want to access it, well, the code has to say, I want to go in the object pool, and I would like to read index number this one. Okay? So now what we have to do is to find our stage 1 string in the object pool. So I'm using for that another disassembler, which is called Jeb, and which is, I'd say, particularly good, especially when you're using Android applications. And Jeb has the particularity to be able to read the object pool. And it displays the strings in the object pool. So, well, this is going to be very helpful. I ask it, well, okay, I'm going to search in the object pool for my stage 1 flag. And it finds it. It tells me, okay, your string is at index 5811. Yeah. So now we are going to have to find some code which is accessing this index 5811. So how do we access it? Well, we've got to use kind of a base register for the object pool, and then an offset. So actually the offset is going to be 8 times this index. Well, yeah. More or less. So it's going to be between this value here and this value there. So, we're going to have to look for that. And then the thing that we have to know is exactly how do we access the object pool in Dart when Dart is assembled. So actually, well, in Dart, you've got a specific register which holds the base of the object pool. In x86-64, it's R15. On other architectures, it's going to be something else. R5, X27. So what we do is that we are going to say, I want to move to R15 plus the offset of the index of my flag multiplied by 8. And this value, I'm going to put it, I don't know, in some other location that I want to keep. So that's what we're doing. We search in Jeb this precise instruction. I use a wildcard for the things that I don't exactly know for instance, in which register I'm going to write to. And it finds a location, this location which is there, and tells me, well, this part, for sure, it is using that, so which means that this location is actually accessing my stage 1 flag. So that's cool. So that was the easy part, okay? Now you're gonna eat a little bit of assembly, but I'm gonna try and make it as, digest as possible. So we go in that function, which is actually using our stage 1 flag. The beginning of this function, well, it looks like, if you're used to disassembling, it's not very new there. It's just the typical prologue for routines. And what you usually do at the beginning of such routines is allocate some space on the stack, which is doing there. And then, well, we see there's a comparison, and this is because, well, again, in Dart, you have another specific register, R14, which is a pointer to the current thread, and it is checking that we are not going above that. Basically, it is doing a stack overflow check, doing that. Okay. So once you know that it's just doing that, you can just skip. You don't really need to jump in there because it will only happen in abnormal cases. You can continue the flow. If you're in another architecture, it's exactly the same thing, except that the registers are going to be slightly different again. So the current thread on ARM64 is x26. And there's even yet something else which is different on ARM64, which is that we're using a custom stack pointer. Okay. X15. So it's not RSP, it's not SP, it's X15 in that case, which is specific to Dart. Now, we continue a little bit in the routine, and we see at some point that it is checking one of the arguments of the routine with the value 2, and then a little later with value 3. So here it's a little bit of guessing, but we guess that actually this argument is probably the stage level, stage 1, stage 2, stage 3. Okay? So we are going to jump to the case where we are checking for stage 3. Then we get to some point where we are dealing with a byte array. I'm going to skip the allocation for now and jump for the where we're loading actually the values in the byte array, and we'll come back to allocation afterwards. So here you have actually the values which are loaded and put in a given offset. So A2 is stored at this offset in here, and then BC, B2, A6, D0, BC, XE2. It's not ASCII characters if you're thinking about that. And to understand a little bit more, then you've got to know another important fact is that in the Dart programming language, you don't have any type for bytes or for characters at all. Which means that the only thing that you have is actually integers. That's the best that we have there. And if you want to do like we currently do in C, which is like have byte arrays with the ASCII codes for each of those, well, actually, you don't have that. You'll have to use the string class, like in Java. And if you want to manipulate that, string buffers or something kind of this way, okay? You don't have byte arrays directly. If you want to do a byte array, you're going to have to do an integer array. So let's say that we want to store character A somewhere. Okay, is it as simple as writing the ASCII code, so 41 in hex, in a given register? Well, of course not, otherwise I wouldn't have written the slide just for that one. And that's because Dart is representing differently small integers which fit in 31 bits and big integers. And this has really quite lots of incidents behind there, because if it's a small integer, the least significant bit is going to be set to 0. What does that mean? It means that it's going to multiply all values by 2. Okay? So actually, if you want to store character A, which is 41 in X, you're not going to write 41, you're going to write 82. Got it? Okay. So, if we go back to our code, we were loading A2, BC, B2, A6. Actually, it means, as all of these are even numbers, it means that they are small integers, which means that actually it's only representing here in hex 51, 5e, 59, and 53. It's still not ASCII characters, well, I mean printable ones. So we go back a little bit to the allocation of the array, and there we see that, well, it's pretty simple, but it's moving this value, 2c. 2c is 44 in base 10. And again, it's an even number, so it's the representation of a small integer, which means that actually it's the encoding for 22. So we are actually here allocating an array, a byte array of 22 bytes. Got it? Now, we've got to actually decrypt it. So here we've got a loop. The loop, here we've got the end condition. Well, it's pretty simple. Have we parsed all our 22 characters yet or not? If we haven't, we still have some work to do. Then for each character, what you have to do is to get the character in the array at this given index. And you see that actually in this assembly code which was generated, well, it handles the fact that it's a small integer or not. So it sees, oh, is it a small integer? It is. Then I've got to divide it by 2. And then once it has been divided, then I have the real value there. And I am doing, in my case, an XOR encryption with a fixed value of 37 in hex. Okay? So we actually have everything we need to do, to get part of the flag already. We have all the values in the array that we had recovered at the beginning. We know that all of these are in representations of small integers, that we can divide them by 2, and that we need after that just to apply an XOR with 37. And you get, find it difficult now. Okay. Which is only part of the flag because we've got some formatting for phone just a little bit afterwards, but this is really the most difficult part. And there you see that the formatting is happening. Well, we have another 2 instructions there, which are actually, so R15 is the register again for the object pool. So it is accessing a given index in the object pool. And if you go and look at that, it's actually index 5810, whatever, which holds the string phone and the curly brackets. So this is going to be concatenated at the beginning of the string, then find it difficult now, and then the last one is the closing bracket, and you get your full flag. Easy, wasn't it? Okay. So congratulations, you solved stage 3. This is good. If you had done it on another architecture, well, it wouldn't have been really more difficult. It's just that it would have been slightly different because the instructions are a little bit different. And also some things are done a little bit differently. For instance, the fact that we are dividing by 2, in ARM32, it's, a shift, so asymmetric shift right. And on ARM64, it's actually copying bit fields and moving it on the right. Okay. So it's the same result. It's going to do a division, but it's really conceptually a little bit different, the way that it's handled. If we summarize a little bit, so what we have different in Dart, we have, well, an object pool. We have small integers which are represented really differently. We have specific registers for example, the object pool, for the VM thread, and a couple of things. We have also a specific stack register on ARM64. And finally, oh, I had forgotten to make you notice this. I don't know if you noticed that. So here, this is the function which is concatenating the string. Okay. And you notice this, we are actually pushing all the arguments on the stack. And this is really unusual. Normally, you push like the first 4 arguments or something like that are put in special registers, and only the further arguments are pushed on the stack. With Dart, everything is pushed on the stack, which is probably not conventional way of doing it. Okay, so that's the last thing, which is pretty kind of strange on Dart. And of course, on top of it, you've got obfuscation. Final part. Well, all of this was for the CTF, but for me, it's interesting in terms of reversing malware, because of course, unfortunately, we're getting more and more samples of malicious samples which are implemented with Flutter. And this is an issue because, well, as you can see, the tools here are not here really up to it. So most of the time before that, we were looking at the samples as opaque boxes and just thinking, well, it's Flutter. I've got to have a look at what is happening before, what is happening after, and probably I'll guess what the malware is doing, which is not a way of doing it, okay? So we really need something better. So here, an example is with Moneymonger, which is actually a campaign which started last year, where it actually affects, I believe, more India. It's like an easy way, which is proposed by the app, to get some money. you get kind of a quick loan, and that, unfortunately, you get scammed all the time, harassed by people who actually got through the application, all the list of your contacts, several pictures and things like that, and they threaten to leak that if you do not reimburse quickly the loan, or sometimes even before the loan hasn't expired yet, sometimes even before you have actually you received the money. So yeah, it was a kind of a big issue there. If we have a look at this code, well, actually, the architecture is kind of two different parts. You've got part of it which is written on the Dalvik Java side, and part of it which sits in Flutter. So basically, they've implemented everything which concerns the user interface in Flutter, and when they wanted to do, for instance, some decryption or encryption, I don't know exactly why, because they could have done it also in Flutter, but probably they already had the routines written in Java, and they wanted to call that on the Java side. So actually, the encryption and the decryption is done on the Java side. But they've got to call that from the Flutter side. So how do we do that? Well, Flutter has a mechanism to be able to communicate with the Dalvik side. It offers kind of APIs, classes, and everything. And on the Java side, you've got to write some code saying that, well, what you want the Java side to do when this or that method is called. You're going to see that on the next slide. Yeah. So this one says that, okay, when on the Dart side, you call a function which is called setConfig, we are going to retrieve the argument which is SMS count, and we're going to edit a shared preferences file. Okay, so this is how it kind of glues the call of a Dart routine with code which is on the Java side. So we have a look in Jeb, and we are searching for this setConfig in the Dart on the Flutter side of the application. We get this, which is looks like the normal prologue of any kind of routine. And if we got a little bit further down, well, actually, it's not really interesting because it's very much like everything which helps probably Dart do the glue and communicate with the Java side. So what's more interesting is to see who is calling setConfig. So we do that, and actually you see it here. Okay, setConfig, and we see that just before that it is calling another routine which is called getSMSCount. And as a matter of fact, it means that getSMSCount is actually retrieving some number and passing that as argument to setConfig. Okay. So what SMSCount does, it actually retrieves that number from another configuration, passes that to setConfig as an argument, and then setConfig actually calls some parts of Dalvik Java code on this side there, and it edits a shared preferences file. Other example is the AES encryption, which is performed. So in the Dart code, you have, at some points, somebody is going to call a function which is called, for instance, AES decrypt. When that happens, well, on the Java side, it says whenever we get AES decrypt called, we are going to retrieve two arguments, password. So this is the symmetric key, and encrypt, with that is the ciphertext. Okay. So where's the key? Well, again, you go in the strings, and you will probably notice pretty quickly that there's a 16-byte key, which is like it's a little bit jumps to the eyes that it's that, and when you use it, it actually works. So it kind of confirms the guess. And with that, you can also use your favorite Frida hook and see what actually it is doing. So actually, what happens is that on the Dart side, you've got an encrypted configuration file. It calls the the Java side, decrypt it, and gives the answer back of the decrypted value which is there. And also, at some other points, the moneymonger malware also wants to send some device information back to the servers. So in that case, it is actually asking from the Dart side, it is asking the Java side to encrypt the information so that it sends encrypted information to the remote server. So, conclusion, for this sample moneymonger, well, all the malicious code was located in the Dalvik part. I hadn't shown the part which are getting the contacts, for instance, receiving the pictures or things like that, because it's on the Java side. And here we were focusing on the Flutter side, okay? The decryption key, however, is on the Flutter side, and we understood kind of how it is communicating between both sides. We do have, since May or June of this year, some samples which are actually implementing the malicious code on the Dart side, directly there. So everything is embarked in the Flutter, in the Flutter environment, which means that it's, of course, a little bit more difficult to digging, but it's possible. And that sample, Fluhorse, is actually listening to incoming SMS and sending that to a remote server. And that's it. Thank you very much for your attention.
Thanks a lot, Axelle, for sharing your amazing experience on reversing Flutter. Nice. Any question in the room for Axelle before we take the break? Back there. He's coming with the
Hi, thank you very much for that presentation. I was wondering, you had in your analysis of moneymonger, Frida hooks, but that was for the Java side, right? Have you encountered any techniques or tools for hooking any of the Dart side?
Yeah, so it's an excellent question. Here I'm using Frida, which is dynamic analysis. It was just to retrieve kind of easily the configuration, whereas everything I have presented for the rest is really static analysis. Yes, we can do that. We can also use the Frida hooks for Dart. By hooking a native function. So in Frida, you can also hook native calls. So if you hook natively this or that, you can get some hooks for the code. But it's sorry, I'm not being very clear. You will be only able to hook like the things which are in the libc or things like that, the low-level stuff, but you won't have access to like hooking. I don't know. We had string concat or AES decrypt or things like that, because those you don't have the symbol, so you don't have the possibility to hook that with Frida directly. It's kind of something which is more like internal to Flutter. So you can do a few things if you're like hooking natively memcopy, stringcat, strcat, or things like that, but you won't have access to the Dart routines with Frida. For now. Maybe it's gonna change. You're welcome.
Thank you. Last question before the break? No. So thanks again, Axelle. We have a 30-minute break.